That is not a rounding error. That is not a laboratory fluke under controlled conditions. That is the real world, sun-to-grid conversion efficiency recorded by Sandia National Laboratories on a solar system you have almost certainly never heard of. For comparison, the panels being sold to American homeowners right now convert sunlight at somewhere between 20 and 22% in the real world. Best case, this technology beat that number by more than 50%. It did it in the New Mexico desert in 2008. It was verified by federal scientists. It was covered in engineering journals. And then it disappeared. Not because it stopped working. Not because it was unsafe. But because a spreadsheet said something cheaper was available, and the financial system was never built to care about the difference. If you have been following this channel for a while, you already know the pattern. The technology that works best is rarely the technology that wins. And nowhere is that more brutally true than in the story of the Dish Stirling engine. A 25 kilowatt solar unit. No silicon. No rare earth metals. No semiconductor degradation. Running on a sealed charge of hydrogen gas and a mirrored dish 11 meters across. Producing enough electricity to power an average American home, with capacity left over from a footprint smaller than a two-car garage. Over 4 million American homes now have rooftop solar. Almost none of them have seen one of these. By the end of this video, you're going to understand why, and what it would actually take to build one. To understand how this machine works, you have to go back 200 years to a stone manse in Kilmeny, Scotland. It is 1816. Steam engines are killing people. Not metaphorically. Boiler failures in Scottish mines and factories are exploding workers with terrifying regularity, and a 26-year-old Presbyterian minister named Robert Stirling has decided that the problem is solvable. He did not have high-pressure steel alloys. He did not have precision machining. What he had was an elegant thermodynamic insight, the kind that feels obvious only after someone else thinks of it first. If you trap a fixed volume of air inside a sealed cylinder and alternately heat one end and cool the other, the gas will expand and contract in a continuous cycle. That expansion drives a piston. No steam. No open combustion. No pressure vessel waiting to rupture. 8 days after his ordination as a minister, Stirling filed British Patent 4081 for what he called a heat economizer, the first practical closed-cycle hot air engine in history. By 1818, a working version was pumping water from an Ayrshire quarry. It ran quietly. It burned any fuel. It needed no water. And then the metals of the era failed under sustained high temperatures. The steam engine industry had too much momentum to care, and Robert Stirling's invention drifted into obscurity for 100 years. It resurfaced in the 1940s, when Philips Research Laboratories in the Netherlands rediscovered the cycle and pressurized it with hydrogen and helium. Power density multiplied by an order of magnitude. But the critical connection happened earlier, in 1872, when a Swedish-American engineer named John Ericsson did something no one had attempted. He coupled a Stirling-type engine to a parabolic mirror and aimed it at the sun. The first solar-powered heat engine in history. He intended it for irrigation pumps in arid climates. The idea was correct. The timing was not. It would take another century for materials science to catch up to the concept. When it finally did, the result was a machine that should have changed everything. Here is how the Dish Stirling system actually works, because the physics are worth understanding. A parabolic dish, shaped like a deep satellite antenna, is lined with curved mirror facets. Those facets reflect incoming sunlight and concentrate it onto a single focal point at the center of the dish. The concentration ratio can exceed 2,000 to 1. That means the receiver sitting at that focal point absorbs 2,000 times the solar energy that would naturally fall on the same area. That receiver heats hydrogen gas sealed inside a Stirling engine to temperatures between 400 and 700 degrees Celsius. The gas expands. It cycles past a component called a regenerator, enters a cooled chamber, and contracts. That expansion and contraction drives pistons connected to a crankshaft that turns a generator. The entire conversion happens mechanically. There is no photovoltaic effect. No semiconductor junction. No electron excitation across a band gap. It is, In the most literal sense, a piston engine running on concentrated sunlight instead of gasoline. The dish tracks the sun on two axes throughout the day, azimuth and elevation, keeping the focal point locked on the receiver from morning to dusk. And when a cloud passes over, the engine slows proportionally. The moment direct sunlight returns, it resumes full output. Because the thermal mass of the receiver holds residual heat during brief interruptions, there is no startup lag. Now here is the number that matters. A standard silicon solar panel is capped at a theoretical maximum of 33% conversion efficiency by something called the Shockley-Queisser limit. Real-world residential panels land between 20 and 22%. The dish Stirling system sidesteps that limit entirely. It converts sunlight to heat first, and heat to mechanical work second. It operates closer to something called the Carnot limit, the absolute theoretical ceiling for converting heat into work. And the gap between those two ceilings is enormous. The performance record is not anecdotal. It is federal. In 1984, the Electric Power Research Institute tested a 25 kilowatt Vanguard dish Stirling unit at Rancho Mirage, California. It posted a net solar to grid efficiency of 29.4%, a world record that stood for over 2 decades. Then in January 2008, Sandia National Laboratories and Stirling Energy Systems ran their Suncatcher unit outside Albuquerque, New Mexico. 25 kilowatts, 38 feet tall, net solar to grid efficiency of 31.25%. The best commercially available photovoltaic panels at that time were running at 15 to 18%. The Suncatcher was producing nearly double the electrical output per square meter of collector area. Think about what that actually means in practice. A single Suncatcher unit could generate 25 kilowatts of peak electrical power from a dish footprint smaller than a standard 2-car garage. At projected manufacturing scale, the levelized energy cost was estimated at 6 to 8 cents per kilowatt hour, directly competitive with the 10 to 14 cents most American households were paying for grid electricity at the time. No water consumption in its basic configuration. Unlike parabolic trough plants that burn through hundreds of gallons per megawatt hour. No internal combustion. No exhaust. No emissions. Its only byproduct was silence. So why is none of this on any rooftop in America? The answer is not a conspiracy. No one voted in a back room to suppress the Stirling engine. The answer is more mundane and, in its way, more depressing. The photovoltaic industry operates on a manufacturing model that Chinese panel producers perfected through massive government subsidies, vertically integrated supply chains, and economies of scale measured in hundreds of gigawatts per year. They drove panel costs below 50 cents per watt. The dish Stirling system, by contrast, is a precision mechanical device. Each unit requires a custom parabolic reflector, a high-temperature receiver, a hydrogen-charged Stirling engine machined to close tolerances, and a dual-axis tracking system. It cannot be stamped out on a production line. It requires skilled assembly, and that means higher per-unit cost at low production volumes, even though its lifetime output per square meter dramatically exceeds photovoltaic. In 2005, Stirling Energy Systems secured a power purchase agreement with Southern California Edison for an 850-megawatt solar farm in San Bernardino County, the largest solar contract in history at that time. A second contract for 709 megawatts followed with San Diego Gas and Electric. The company had Sandia's test data, federal backing, 2 record-breaking prototypes, a clear path to scale. Then the price of photovoltaic panels collapsed. Between 2008 and 2011, Chinese subsidies drove panel prices down by nearly 75%. Project developers who had committed to dish Stirling began switching to photovoltaic because the upfront cost per watt was lower, even though the lifetime efficiency was worse. In late 2010, a power holding company bought the Calico Solar project and converted 750 of its 850 megawatts from dish Stirling to photovoltaic. The federal loan guarantees the project's needed never materialized. On September 29, 2011, Stirling Energy Systems filed for Chapter 7 bankruptcy and liquidated its assets. $100 million in private investment evaporated. No one conspired to kill the Stirling engine. The most efficient solar technology ever field tested was dismantled because a subsidized competitor made it temporarily cheaper to choose the less efficient option. No federal incentive program, no investment tax credit structure, and no utility procurement process was designed to reward conversion efficiency. They reward cost per watt at the point of installation. That single metric made photovoltaic panels the default, and it sidelined the dish Stirling system with the ruthless indifference of a spreadsheet. Now, if you want to build one, here is what that actually looks like. There are two practical paths for a small-scale build. The entry point is a repurposed satellite dish lined with reflective film or mirror tiles. A standard 6-foot dish can concentrate enough solar flux to drive a low-temperature differential Stirling engine and generate between 50 and 200 watts of electrical power, depending on engine quality and the precision of the reflector surface. The reflective film runs between $20 and $40. A small machine Stirling engine suitable for solar demonstration costs between $300 and $600 from specialty manufacturers. Total cost for a functional proof of concept sits between $400 and $800, producing enough power to charge a battery bank or run a small DC load. The critical variable is focal precision. The reflector must concentrate sunlight within a spot no larger than 2 to 3 inches in diameter at the receiver. That means the dish surface needs to approximate a true parabola within a few millimeters of accuracy. If that alignment drifts, the efficiency drops fast. For a serious off-grid installation targeting household-scale output, the approach changes significantly. You are looking at a custom fabricated parabolic dish between 5 and 7 meters in diameter, paired with a high-temperature kinematic Stirling engine rated for 1 to 5 kilowatts. A dish of this size needs a concrete pedestal foundation, a dual-axis tracking mount driven by a small DC motor and controller, and a receiver cavity designed for operating temperatures above 500 degrees Celsius. Total installed cost for a professionally built 1 to 3 kilowatt dish Stirling system runs between $8,000 and $20,000 depending on engine sourcing, fabrication quality, and tracking system complexity. That compares to roughly $12,000 to $18,000 for a rooftop photovoltaic system of equivalent rated capacity. But the dish Stirling system will produce significantly more kilowatt hours per year from the same rated power, because its conversion efficiency is 50 to 80% higher under direct sunlight. If you want to push this